Hello, so welcome to OTHM Level 7 Diploma in Environmental and Sustainability Management. So today we're going to talk about environmental science and the energy transition. So this is learning outcome 1, so understanding the physics of the energy-related carbon cycle and its impact on temperature. So I'm just going to go over the unit aims. So let's have a look. So the aim of this module is for students to understand the physical underpinnings of energy systems, development of alternatives to fossil fuels, both renewable and non-renewable, and their dependence on energy storage and grid management. A particular focus of this unit is given to the sustainable technologies that can harvest solar and wind energy. Students will also explore and review national and international policies and different pathways to reduction of carbon emissions from energy systems. So for this session, we will cover, so number 1, so we will go over how we need to understand the physics of the energy-related carbon cycle and its impact on temperature. So as the assessment criteria, so the learner needs to show that they can, so for 1.1, identify and differentiate what we mean by the different scope areas 1, 2 and 3 of the carbon footprint. 1.2, learners should be able to describe the carbon cycle related to energy uses and the meaning of the term Anthropocene. 1.3, explain how carbon footprinting differs from life cycle assessment. They are very different methodologies and we will cover that today. 1.4, explain how to read key intergovernmental panel on climate change, so known as the IPCC, so those reports, and how to apply the knowledge, that knowledge within the IPCC on a published report. 1.5, analyse the physical principles of energy technologies. Oh gosh, sorry about that. Down. So analyse the physical principles of energy technologies and how energy technologies were historically used. And 1.6, we will look at how to analyse the work of the IPCC and its role in driving international efforts to tackle climate change. Okay, so I will bring up the slides now. Okay, so the aim of this unit is for students to understand the actual physical underpinnings of energy systems, the development of alternatives to fossil fuels for both renewable and non-renewable, and their dependence on energy storage and grid management. A particular focus of this unit is given to the sustainable technologies, harvesting solar and wind energy. Students should also explore and be able to review national and international policies and the different pathways to reduction of carbon emissions from energy systems. So for learning outcome 1, the indicated content is based on the below. So we have the physical principles of energy technologies and the energy-related carbon cycle. We'll go over that. The history overview of energy use. There is a historical background to energy use, and it's important to understand where how that's impacted where we are today and its connections to global policy, with specific focus on indigenous energy sources and their reintroduction. We will cover a brief history of coal and oil. The point of this is to A, appreciate old and indigenous technologies that may come back, be revived and modernised. B, appreciate that the current energy systems didn't just appear mature, they've been developing over time, and renewables are sometimes dismissed as inefficient. And we'll cover the information around that and those thoughts. Coal and oil also started as inefficient many years ago. So, and we will introduce what a carbon footprint is, so the different free scopes of CO2 equivalent and what is the CO2 equivalent, what does that mean? We will cover the carbon budget and outsourcing of carbon emissions, and then we will explore the differences between a carbon footprint and life cycle assessment, or it's known as life cycle analysis. Okay, so it's really important to understand the physics of the energy-related carbon cycle and its impact on temperature. So when we talk about the carbon cycle in a energy context, we're looking at how carbon moves between the atmosphere. Carbon has always existed, and we need it. It's part of how the planet operates. But the problem we're in at the moment is humans have disrupted this balance, and we will go over. I'll show you a short video soon which really explains this. So at its core, the carbon cycle is a natural process. I think it's really important that we understand it is a natural process. I mean, we do need the carbon cycle, and it's kept the planet's temperature relatively stable for thousands of years. It's given life to us on this planet for thousands of years again. So carbon dioxide, also known as CO2, methane, CH4, and other greenhouse gases, help trap heat in the atmosphere, preventing the Earth from losing all of its infrared radiation back into space. So essentially, it means that greenhouse gases exist to store energy and heat and warmth, which is a natural process, which is what we need to support all life. So it's the natural greenhouse effect, and it's why the planet is warm enough to support life. So the physics is clear when we break down how energy is absorbed and emitted. The sun sends shortwave solar radiation to Earth. The surface absorbs some of this energy, so it's absorbed into the planet, and then it re-emits this as a long-wave infrared radiation. So the greenhouse gases in the atmosphere absorb part of this outgoing radiation, and it gets re-radiated in all directions across the planet, including back to the surface. So this additional heat retention raises the average global temperature. CO2, carbon dioxide, is the most important of these greenhouse gases because it stays in the atmosphere for centuries, and its concentration is rising steadily due to human activity. So we know that carbon dioxide has always existed, we need it, but the problem is that due to human activity, the levels of carbon dioxide have accelerated, and it's caused the temperatures across the planet to rise excessively. So most of the CO2 increase comes from energy use. So when with fossil fuels that we use, like coal, oil, and natural gases, when those are burned, the carbon that was locked away for millions of years underground, which then becomes used for fossil fuels, which we use for energy. This is natural carbon sinks, and basically across oceans, forests, and soils, carbon is stored, and it's a wonderful process, a wonderful thing. In the ice caps, you will find that it stores methane. So it's a natural process, and it just ensures that we can't. It protects the planet, so it ensures that the greenhouse gases don't build up in the atmosphere, they will be stored. So this shift alters the radiative balance of the climate system. So the more CO2 that accumulates across the planet and the more infrared radiation that gets trapped, this means that temperatures are increased excessively, and this is a problem that we have today. So I'm going to show you a short brief video that really does explain this and the greenhouse cycle.
Greenhouse effect is a natural phenomenon. Sunlight falls through the atmosphere to the Earth, heating its surface. Not all of the heat remains there, however. Most of it is emitted as long-wave thermal radiation from the Earth's surface into space. In this respect, the gases in the Earth's atmosphere play an important role. For the most part, they allow the short-wave solar radiation through, but the long-wave thermal radiation which is coming from the surface is partly absorbed by these gases, which means that additional heat is stored in the atmosphere, like in a greenhouse. As a result of human activity, more and more of these greenhouse gases are finding their way into the atmosphere, strengthening the greenhouse effect. The additional heat is causing climate change, with the Earth literally heating up, and with some huge consequences for the environment and people. Carbon dioxide has by far the greatest share of anthropogenic greenhouse gas emissions, which means emissions that are caused by human activity. This mainly arises when fossil fuels such as coal, crude oil, or natural gas are burned. To be able to better summarize and analyze the effects of these gases, their global warming potential can be expressed in the form of CO2 equivalents. This shows how much more an individual greenhouse gas contributes to global warming in the next 100 years, compared with the impact of CO2. Accordingly, the impact of methane is 25 times greater than CO2. Therefore, in the first 100 years of its emission, 1 kilogram of methane contributes 25 times more to the greenhouse effect than 1 kilogram of CO2. In Germany, methane largely arises through agricultural livestock farming and the waste sector. The impact of nitrous oxide is 298 times greater than CO2. This mainly arises during the production and use of fertilizers and in the chemical industry. Although fluorinated gases only account for a very small proportion of total emissions, some of them have an extremely potent greenhouse impact. The CO2 equivalent of sulfur hexafluoride, for example, is 22,800. F gases are used as coolants and extinguishing agents, as propellants and in solvents, among others. In Germany, most greenhouse gas emissions arise when fossil fuels such as oil or coal are burned to generate energy. The primary source in this area is the energy industry, for example, the generation of electrical power and heat. This is followed by transport, industrial furnaces, private households, and the commercial, retail, and service sectors. Other emissions are caused by the production processes in industry, agriculture, and waste management. If emissions from energy production are broken down and the share accounted for by industrial furnaces and production processes are added together, it is clear that industry, as a whole, is the second biggest source of emissions. All of these emissions intensify the greenhouse effect. For this reason, it is necessary to reduce the emissions of greenhouse gases as far as possible, or, ideally, for them to be stopped entirely. Important political measures include a transport revolution, for example, more walking, cycling, and use of public transport, a switch to electromobility, and overall significantly fewer cars and lorries on the roads. More efficient and more economical fertilization and lower livestock numbers in the area of agriculture. And of course the energy revolution, i.e. the complete phase-out of coal-fired power generation in favour of renewable energies and the efficient and economical use of energy. Fewer man-made gases mean less warming, and every reduction in emissions makes an important contribution to the protection of the climate.
Okay, so I hope that was helpful. So as the video explained, the greenhouse effect is a natural phenomenon, but we need like we need the Earth to have heat for life on Earth, but the greenhouse gases have accelerated and trapped too much heat within the planet, which has meant that we get excessive temperature rises. And this is why we need to look at reducing the greenhouse gases, and there's different things that we can look at that the video talks around, particularly transport use, agriculture. So we'll go into that later on, but I thought that was a really good video that showed the whole process there. So what makes energy-related carbon cycle particularly important is the feedback loops it triggers. So warmer oceans absorb less CO2, so more stays in the air. So it means that it has a knock-on effect that we then are losing the oceans for that storage for CO2. So melting ice reduces the Earth's reflectivity, so the planet absorbs more heat, which in turn adds to more warming of the planet. Permafrost thaw releases methane, which traps even more heat. So it's really important. We need our oceans. We need our ice caps. They're really important to store greenhouse gases so that we don't continue this excessive warming of the planet. So all of these feedbacks amplify the original warming driven by fossil fuel emissions. In simple terms, the physics is straightforward, and more carbon in the atmosphere means more trapped heat. Human energy systems have overloaded the natural carbon cycle, upsetting a balance that has been stable for millennia. As a result, global temperatures continue to rise. So this increases the frequency of extreme weather, accelerating sea level rise, and putting pressures on ecosystems and biodiversity. It's all connected, and there's something called the tipping points that all get triggered, which we will talk about on the next session. So it's really important to understand the link between energy usage, carbon, and temperature as a foundation for when we do look at any kind of climate policy, renewable energy, or sustainability planning. So 1.1, Learning Outcome 1, this is around identifying and differentiating what we mean by the different 3 scope areas, so scope 1, 2, and 3 of the carbon footprint. So when we look at an organisation's carbon footprint, it's a way of looking at how much greenhouse gas is being produced across an organisation, and the methodology that is used commonly is to break it down across the 3 different scope areas. So these different 3 scope areas help us separate what the organisation directly controls. So what does the organisation have agency and control to take action on, which greenhouse gases, and it just allows transparency and allows us to look at which particular greenhouse gases across the 3 scope areas are particular high, so then we can make a plan to reduce those. So so these scopes help separate what the organisation directly controls, what it indirectly causes through energy use, and what it influences across its wider value chain. So scope 1 emissions are the easiest to understand because they come from sources the organisation directly owns or operates. So this is the area, the scope, the first scope area is that organisations probably have more control to get a grip of, essentially. So this includes fuel burned in company vehicles, gas used from heating a building, and emissions from on-site equipment or manufacturing processes, so a boiler, for example. If the organisation physically burns the fuel or runs the machinery, the emissions fall under scope area 1. So the second scope area is these emissions are indirect but are closely linked to the organisation's operations. So these are the emissions that are created by the generation of electricity, heat, steam, or cooling that the organisation buys in. So it doesn't directly control, it will source from another energy supplier, for example. So even though the organisation isn't generating the energy itself, it causes those emissions by using the energy. So a simple example is electricity drawn from the national grid. So the emissions happen at the power station, not in the actual organisation's premises, but the organisation still is responsible for them because it actually sourced that energy. So when an organisation is looking to reduce energy usage and look at the different scope areas, a great idea is to look at the bills of the building and to look where you'll be able to see on the bill from the energy supplier the breakdown of where the energy has come from. So that's a good way to have a look at that. So scope 3 emissions are everything else in the wider value chain. So they're the hardest to measure. So this is when it gets quite tricky. You're looking at your suppliers. So this is why procurement has such a vital role to play within organisations, because you then can see where where you procure, where you get your services from and how they use energy. So they are the hardest to measure and usually the largest share of the company's footprint. So Scope 3 covers all the emissions the organisation influences but doesn't directly control. So that includes emissions from suppliers producing raw materials, employee commuting. So, for example, any travel that employees may take back and forth to an office, be it by train, tram, car or bus, business travel, waste disposal, product transportation. So if you are an organisation that produces products and has to transport these products, that then has a carbon footprint. So the use of the company's products by customers and even the emissions created when those products reach end of life. So when you're looking at it from cradle to grave, so where does the product, what happens to the product when it's been used and it is no longer of any use? How is that disposed of? So with Scope 3, the key idea is connected but not owned. So that's a really good way to have it in your mind. So the easiest way to keep the difference in mind is this. Scope 1 is direct. Scope 2 is indirect but energy related. And Scope 3 is everything else up and down the value chain. So most organisations discover that Scope 3 overwhelmingly dominates their footprint, which is why serious carbon reduction strategies have to look beyond their own building and vehicles and dig into purchasing, supply chains and product design. Even within an accounts team and finance within financial teams, you've got really good insight into where the money's going and which products are being used. So looking at your accounts is a really good way to look where the money's going and if it is impacting to greenhouse gases, if it's connecting and driving those greenhouse gases. I'm going to try and find a short video around the 3 different scope areas. This is a good one. Okay, I'll show you this one.
Understanding your organization's carbon footprint is a crucial step towards reducing your company's climate impact. The company's carbon footprint is classified into 3 categories of emissions: Scope 1, Scope 2, and Scope 3. But how can we differentiate them? Let's begin with Scope 1. It includes direct emissions from a company's owned or controlled sources, such as on-site energy like natural gas and fuels, refrigerants, furnaces, as well as emissions from fleet vehicles. Also included in Scope 1 are process emissions, which are released during on-site manufacturing. Now we come to Scope 2 emissions, which are your company's indirect emissions from purchased energy. According to the GHG protocol, Scope 2 represents one of the largest sources of greenhouse gas emissions globally. In that way, it generally offers an opportunity to significantly reduce emissions. Scope 2 emissions mostly include indirect greenhouse gas emissions from purchased or acquired energy like electricity, steam, heat or cooling, generated off-site and consumed by the reporting company. Lastly, we come to Scope 3 emissions, the indirect value chain emissions of a reporting company. According to the US Environmental Protection Agency, Scope 3 emissions are the result of activities from assets not owned or controlled by the reporting organization. These emissions can represent the largest portion of its greenhouse gas emissions inventory and are the most challenging ones to calculate. The GHG protocol divides Scope 3 emissions into upstream and downstream emissions. Upstream emissions are related to purchased or acquired goods and services. These upstream emissions are classified in 8 categories, which are purchased goods and services, capital goods, fuel and energy related activities, upstream transportation and distribution, waste generated in operations, business travel, employee commuting, and upstream leased assets. Downstream emissions are related to sold goods and services and emitted after they leave the company's ownership or control. Downstream emissions fall into 7 categories. Downstream transportation and distribution, the processing and use of sold products, as well as the end-of-life treatment. It also includes the emissions of downstream leased assets, franchises, and investments. An experienced partner can help you to develop a full corporate greenhouse gas emissions inventory that includes scopes 1, 2, and 3. This inventory provides a baseline and gives you the opportunity to continuously measure and reduce your carbon footprint to make the transition to a net zero economy. Kick off your climate action strategy now.
Okay, so I hope that was helpful. It's really good to kind of try to map out the different scope areas. So if you do get an opportunity, you could put 3 different categories for scope 1, scope 2, scope 3, and start to map out the different scope areas across your organisation. Okay, so learning outcome 1.2. So this is around describing the carbon cycle related to energy uses and the meaning of the term Anthropocene. So when we look at the carbon cycle in the context of energy use, we're talking about how carbon naturally moves between the atmosphere, the oceans, living organisms, and the Earth's crust, and how human activity disrupts that balance. So in a natural state, in its most natural state, the carbon cycle works like a closed loop. So you have plants that absorb CO2 through photosynthesis, animals and humans release CO2 through respiration, the ocean absorbs and releases carbon, and long-term geological processes lock carbon away underground. For thousands of years, this system has kept atmospheric CO2 at relatively stable levels, so it's worked, it has worked. Since the use of energy use, especially fossil fuels, such as oil, coal and natural gas, because these are made of carbon that's been stored underground for millions of years. So when we burn these fuels for electricity, heating, transport or industrial processes, that stored carbon is released suddenly as CO2. So this adds additional CO2 to the atmosphere, so much faster than natural systems are used to and can absorb. So usually, as we mentioned earlier, the nature has a great way to absorb additional CO2, but because of the burn of fossil fuels, it can't work in harmony because it's happening at such a massive rate that it's unnatural and it can't keep up. So forests and oceans do help, but they can't keep pace with the scale of emissions. So as a result, the concentration of CO2 has risen steadily. This matters because CO2 is a greenhouse gas. It traps heat that would otherwise escape into space, intensifying the natural greenhouse effect and raising global temperatures. So the more fossil fuels that we burn, the more carbon we're pushing into the atmosphere, and the greater the warming effect becomes. It's a physical, simple chain. Energy use leads to CO2 emissions. Emissions disrupt the carbon cycle, and a disrupted carbon cycle changes the climate. So a way to explain this is through the word the Anthropocene. So this explains the shift. So it's a term that scientists have developed to describe the current geological era in which human activity is a dominant force shaping the planet's systems. So in other words, humans have altered the Earth so significantly through energy consumption, deforestation, industrialization, agriculture, and large-scale resource extraction that our impact now rivals natural geological forces. So this has meant rising CO2 levels, melting of the ice sheets, which we need for carbon capture and for methane storage, etc. So ocean acidification and mass species loss are all markers of this human-driven age. So we use Anthropocene to capture one simple idea: the planet no longer evolves only through natural processes. So our human behaviour, especially the way that we produce and consume energy, is now one of the most powerful drivers of environmental change. So I think once we understand the impact of energy usage and how it contributes to greenhouse gases and climate change, we can start to look at alternative energy use. So understanding this concept helps explain why climate policy, energy transition and sustainability have become global priorities and need to be a priority for organisations as well. Organisations, have potentially have a massive influence in driving this change. So when we look at different types of measuring greenhouse gases, you have carbon footprinting and you have life cycle assessment. Now these two methodologies are quite different, and we'll go over that now. So carbon footprinting and life cycle assessment are related, but they're not the same thing. So when we are to carry out a carbon footprint, we're focusing specifically on measuring greenhouse gas emissions. So it's a targeted assessment that looks solely at how much CO2 and other climate relevant gases are produced during certain activities, processes, or across an organisation. So it's all with the aim to quantify the emissions so that we can understand the climate impact, and then we can start to identify where we can potentially make reductions. So life cycle assessment takes a much wider view. So this not only looks at greenhouse gases, but an LCA will examine the full environmental impact. So it'll of an impact of a product, or service from start to finish, from cradle to grave, they call it. So that includes raw material extraction, manufacturing, transport use and disposal. It can look at a broad set of different environmental categories such as energy use, water consumption, toxicity, land use, resource depletion and pollution. So an LCA will map out the entire potential environmental burden across the whole product's whole life cycle, so not just the carbon emissions, not just the greenhouse gases. So a way of looking at this is to look at one of the key differences is the scope. So a carbon footprint can be narrow or broad depending on what we choose to measure. So for example, the carbon footprint of a single product or building or transport system or an organisation will focus only on the emissions. An LCA by design is comprehensive and multidimensional. It will look at various different environmental inputs and outputs. So another key difference is purpose. So carbon footprinting is mainly used to support climate strategies, reduction targets and reporting frameworks like Scope 1, 2 and 3. In contrast, an LCA is often used for product design, sustainability comparisons, regulatory compliance and understanding trade-offs across different environmental factors. So for example, a product might have a low carbon footprint but create higher water use or waste impacts, which only an LCA would reveal. So it is a comparison of different environmental impacts. So to put it simply, a carbon footprint measures climate impact, while in contrast, an LCA measures overall environmental impact across the full life cycle. So both methods are useful, but they'll answer different questions. Okay, so the next area we're going to look at the IPCC. So what is the IPCC? So the IPCC is the Intergovernmental Panel on Climate Change, which was created around 1988 by the UN. So it's an impartial body, which is a group of international scientists that will do peer-reviewed scientific studies excuse me, that will be relied upon by international governments to make informed decisions around climate policy. If you think of it as a kind of bridge between the climate science and global decision making, that's a really good way to look at it. So when we kind of look at the IPCC reports, and then we apply that knowledge to a published report, it's important to remember the following things. So this is for 1.4, learning outcome number 4, 1.4, sorry. So when we read an IPCC report, the first thing we need to consider is that these documents are scientific summaries, not opinion pieces. So essentially they'll pull together thousands of peer-reviewed studies that will present what the global scientific community agrees on. So it's science-based because they're dense. We're going to focus now on a few core elements that matter most for understanding climate risks and translating the science into real-world decisions. So if we look at starting with the Summary for Policymakers, so the SPM. So the Summary for Policymakers is written in plain language and highlights the key findings of how the climate is changing, what's driving the change, and how severe the impacts are expected to be, and what mitigation or adaptation options exist. So the SPM gives us a structure and the headlines, so we know what to look for in the detailed sections. So the second part of this is to look for the confidence levels and likelihood statements. So the IPCC reports use specific language like high confidence, very likely, or medium confidence when they draw conclusions. So this isn't guesswork, there is a meaning behind these categories. It's a structured way of telling us how strong the evidence is. So when I read a finding, I pay attention to these qualifiers because they tell us how robust the science is behind each statement. So anything marked very likely, so 90 to 100% probability or high confidence, has broad scientific agreement across the globe. So we know that it's credible. So for the third section, so the focus is on the drivers of change and emissions pathways. So each major report explains why the climate is warming, how emissions are distributed across sectors, and which pathways, like the famous SSP2 to 4.5 scenarios, lead to different levels of warming. So there are different scenarios to different levels of warming, so it's important to understand there's different ways of getting there. So these pathways are useful for planning. So if I'm working in energy, education, or policy, the pathways will tell us how fast emissions must fall to limit warming to 1.2 degrees or 2 degrees. So for section 4, examining the impacts and regional assessments. So the IPCC doesn't speak only in global averages. There are sections that break down impacts by continent or region. So then it gets a bit more complex. So this helps us take the global science and understand what it means locally. So heat waves, flooding, crop losses, economic disruption, and other expected changes. So reading these regional chapters helps me connect global findings to real world risks. So it's a global problem, but the local impacts will be different depending on their geography. So section 5, so using the figures, charts, and summary tables. So graphs are often clearer than texts. Temperature, I'm going to zoom in a little bit more here, sorry about this. So temperature projections, emission trajectories, impact timelines, and carbon budgets are all visualised. I use these visuals to reinforce my understanding to explain the findings to others who may not read the full report. So here's an example of how we'd apply this knowledge to a published report. So to show practical application, here's an example of how we would use IPCC principles when reviewing any published climate-related report. So for example, it could be a government climate strategy or a CSR report, corporate social responsibility report, or an NGO analysis. So for example, applying the IPCC knowledge to a UK government net zero report. So you would check the alignment with the IPCC pathways. So if the report claims to support a 1.5 degrees target reduction, excuse me, but only shows modest emission cuts, I compare this against IPCC pathways. So the IPCC says the global CO2 needs to fall by around 45 degrees by 2030 to be aligned to the 1.5 degrees path. So if the report's targets fall short, we can then identify the path. So we know that we need to be on target for a reduction of 45 degrees of CO2 emissions by 2030 in order to reach the target for 1.5 degrees. So assessing whether it addresses major emission sources. So the IPCC identifies energy, transport, industry and agriculture as the biggest emitters. So we know they're the biggest impact areas. So we can use this as a benchmark. So if the published report ignores one of these sectors, we know that it's not reliable because we know these are the biggest impact areas. I'm just going to zoom in a little bit more. So evaluating its assumptions using IPCC data. So if the report relies heavily on technologies like carbon capture or hydrogen, we can cross-check that with the IPCC assessment of their readiness, scalability and risks. So this will help us judge if the report is realistic or overly optimistic. Typically we know that carbon capture, so any organisations that do rely on carbon capture can be seen as being a weak form of sustainability because it's focusing on the aftermath rather than, mitigation, rather than reducing carbon. It's look at kind of dealing with the carbon after it's been released. So yeah, it's good to check where the IPCC stands on that. So number 4, we use the IPCC's risk and impact findings. So if the published report discusses climate impacts, we can assess whether it's consistent with what the IPCC says about heat, flood risks, sea level rise or ecosystem changes. So anything that downplays risks below the IPCC range is a red flag, so that's important to be aware of that. So the IPCC is a really kind of reliable group body to compare any kind of strategy from any organisation that is looking to reduce its impact when it comes to carbon emissions. So checking the transparency of evidence. So the IPCC summarises peer-reviewed science. So when we can read a report, we expect references, data sources and clear methodology. So if they're missing, we know that the claims aren't grounded. So we know that any kind of report that doesn't source reference where the data or the information has come from, or it doesn't allude to the methodology or any limitations that may be in place around the methodology that was used to come to scientific conclusions, we know that it isn't a reliable piece of information, and we should challenge that and criticise and be critical, sorry. So 1.5, so this is learning outcome 1.5. So this is all around analysing the physical principles of energy technologies and how energy technologies were historically used. So there is a history for different technologies when it comes to energy. So we will go over the physical principles of different types of energy in this section. So I'm just going to zoom in a little bit. So when we analyse energy technologies, it's good to have a look at the physical principles behind them, because every energy system, old or modern, depends on basic laws of physics. So historically we know that societies used whatever energy forms were easiest to harness with the technology available at the time. So over time, improvements in engineering, materials and scientific understanding have changed how effectively we can convert energy from one form to another. So the physical principles. So generally most energy technologies rely on really similar, they have a common physics behind them. So the conversion of energy from one form to another. So energy cannot be created or destroyed, but it can change form. So early systems used mechanical energy directly, such as water wheels converting kinetic energy or flowing water into rotational motion or from milling grain. A modern power station works on the same kind of principle, but is on the scale of it is much bigger. So burning fuel to create heat, for example, turning water into steam and driving a wind turbine to produce electricity. So there are two examples. So heat and thermodynamics. So fossil fuel technologies rely on combustion. So when we burn coal, oil or gas, chemical energy is stored in the fuel and the fuel is converted into heat. So that heat expands into steam or gas, which then will drive the turbine. So the second law of thermodynamics tells me these conversions always involve a loss, which is why no power plant is ever 100% energy efficient. So efficiency improvements over the last century come from better materials. So we have got better over the time in terms of energy efficiency, but we can do better. So this has happened through, from better materials that are being used, higher operating temperatures and improved turbo design. So physical principle number 3 is electromagnetism. So electricity generation is based on Faraday's law. So when a magnetic field moves relative to a coil of wire, it induces an electric current. So whether the turbine is powered by steam, wind, falling water or a gas jet, the end goal is to spin a generator. This hasn't changed. This technology still exists. So section 4 is all around solar radiation and semiconductor physics. So solar energy relies on the photoelectric effect. So sunlight hits a semiconductor, freeing electrons and generating direct current. This physics was discovered in the 1800s, but took over 100 years to turn it into efficient solar panels. Section 5. So nuclear technology works by splitting heavy atoms like uranium. There's a lot of contention and debate around nuclear energy at the moment in terms of the risk associated with it to be a sustainable use of energy in the future and now. So the heat that produces steam drives turbines, and the physics comes from the conversion of mass into energy, and is described by Einstein's equation E equals mc2. So there is a history to the use of energy technologies. So even before early human societies, before industrialization, energy systems were almost fully renewable, but extremely limited. So people used human muscle, animals, firewood, wind, and water power. These sources were local, low density, and constrained, were seen as constraining economic growth. So the Industrial Revolution, so everything changed when steam engines arrived. By burning coal to produce mechanical power, factories no longer depended on rivers or manual labour. So coal became the backbone of industry because it was energy dense and abundant. This era marked the start of the large-scale carbon emissions. So this is a really important moment within the development of energy technology. And you can see, I'm going to show you another video now, because you will see a correlation between the warming of the planet and energy usage and change. Okay, where's it gone? Sorry about this. I'm going to show you a short video by the National Geographic.
Human activities, from pollution to overpopulation, are driving up the Earth's temperature and fundamentally
sorry about this. Seems to have frozen.
Around us are driving up the Earth's temperature and fundamentally changing the world around us. The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than a third since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years. Climate change has consequences for our oceans, our weather, our food sources, and our health. Ice sheets, such as Greenland and Antarctica, are melting. The extra water that was once held in glaciers causes sea levels to rise and spills out of the oceans, flooding coastal regions. Warmer temperatures also make weather more extreme. This means not only more intense major storms, floods, and heavy snowfall, but also longer and more frequent droughts. These changes in weather pose challenges. Growing crops becomes more difficult. The areas where plants and animals can live shift, and water supplies are diminished. In addition to creating new agricultural challenges, climate change can directly affect people's physical health. In urban areas, the warmer atmosphere creates an environment that traps and increases the amount of smog. This is because smog contains ozone particles, which increase rapidly at higher temperatures. Exposure to higher levels of smog can cause health problems such as asthma, heart disease, and lung cancer. While the rapid rate of climate change is caused by humans, humans are also the ones who can combat it. If we work to replace fossil fuels with renewable energy sources like solar and wind, which don't produce greenhouse gas emissions, we might still be able to prevent some of the worst effects of climate change.
Oh, sorry about that. Okay, so going back to the slides, I hope that was helpful. Okay, so we know that burning coal has massively increased temperatures across the globe and has many impacts for the planet and for people too. So everything changed when steam engines arrived. By burning coal to produce mechanical power, factories no longer depended on rivers or manual labour. Coal became the backbone of the industry because it was energy dense and abundant. So as we've said before, this era marked the start of a large-scale carbon emissions. So the age of electricity, so in the 19th and early 20th centuries, societies moved from mechanical energy to electrical energy, so hydro power stations, coal power plants and late gas turbines made it possible to generate electricity centrally and distribute it through grids. So this completely changed how people lived and worked, and it had many positive impacts for people. But it's important to remember that there is positives, but there is kind of limitations to that as well. So in the 20th century expansion of oil and gas, oil-powered internal combustion engines revolutionised transport. So cars, aviation and shipping became global systems. Gas replaced coal in many power stations because it burns cleaner and more efficiently. So these fuels are really cheap and convenient, which encouraged the dominance. So the market enabled them to be cheap and convenient. So that's why we've seen the growth of them and why they've been used so much. So the late 20th century, we saw the rise of nuclear energy. So nuclear power has emerged as a high energy density alternative to fossil fuels. It offered huge electricity output with low operational emissions. although it came with political, environmental and safety debates. So there is a lot of contention and challenges with the use of nuclear power. And you'll find with each alternative energy, there will be pros and cons to that as well. So the modern era, so renewables and storage, wind and solar have grown rapidly due to better materials, cheaper manufacturing and smarter grid systems. So battery storage, hydrogen and heat pumps are now reshaping how societies use and store energy. The physical principles behind them aren't new, but modern engineering makes them viable at scale, so they can be scaled up. Okay, so to summarise, across history, societies have moved from simple mechanical systems to complex high-energy technologies. The physics hasn't changed, energy is still converted, transferred and lost along the way, but our ability to exploit those principles has grown. So there's been a technology shift, and technology has driven changes for the economy as well, living standards and environmental impacts. So technology, it's all connected, all interconnected, and fossil fuels have become central to a lot of systems across the planet. We rely heavily on fossil fuels. So today's transition to low carbon systems is another step in that long technological train driven by both physics and necessity. So it's important to have an awareness of all those different interactions. So 1.6, so this is around analysing the work of the IPCC and its role in international efforts to tackle climate change. So there's been, again, with the IPCC, there's been a lot of different ways of thinking around its purpose and how, what does its role mean and how successful has it been in reducing global temperatures. So when we analyse the work of the IPCC, we can start to kind of really think about how it's a scientific body, that it doesn't run experiments, enforce policy or advocate for specific political positions. It's meant to be an impartial body, so it's meant to present and assess existing scientific research on climate change, and that's why it has been seen to be reliable and a force for change, to drive change across the planet. So it's evidence-based, and it reviews what's happening to the climate, what is driving the changes, if it's human-driven, what are the impacts expected and what options exist to respond. So this makes the IPCC the global reference point for climate knowledge. So the IPCC operates by bringing together thousands of scientists from across the world who review peer-reviewed studies and synthesise the findings. The work is broken into three main working groups. So this is the structure of the IPCC. So you've got working group 1, grouping work 2 and grouping work 3. So group 1 will focus on the physical science, the actual scientific foundation of climate change. So it looks at, this group will cover temperature rise, sea level change, carbon budgets and atmospheric physics. The second working group looks specifically at the impacts, the risks, vulnerability and adaptation, so how we respond. So we're kind of at a point now where, we know climate change is already happening. We're seeing many negative impacts across the world. So we are kind of looking at ways that we can adapt and respond and make the planet a safer place. So this is where we can look at materials for regional effects, food security, water stress, ecosystems and human settlements. So the third working group of the IPCC focuses on mitigation. So mitigation is seen as a strong form of sustainability, as it is looking at how we can actually reduce the emissions rather than deal with the aftermath of the emissions. So this is a really good kind of way to limit greenhouse gases and climate change. So this looks at how emissions can be reduced across sectors like energy, transport, buildings and industry. So on top of these, the IPCC produces synthesis reports which combine everything into an accessible overview. So each report is created through a strict review process involving scientists, governments and independent reviewers. So this ensures that findings are transparent, challenged and agreed upon internationally. So this is I would say it's the most trusted international body when it comes to climate change research. So the final language in the summary for policymakers is negotiated line by line, which why the IPCC is seen as authoritative, and every science signs off the science as well. So why does the IPCC matter so much internationally? So the IPCC doesn't set out a policy, but it works to underpin almost every major climate agreement and national strategy. So when we look at climate action, global climate action, the IPCC's influence shows up in several ways. So if we look at the background for international agreements, we've got the 1992 UN Framework Convention for Climate Change, the Kyoto Protocol and the Paris Agreement all heavily rely on the IPCC science. So you've got the famous Paris target, which aims to limit warming to 1.5 degrees or well below 2 degrees, which we have unfortunately passed. I think last year we did reach just over 1.5 degrees for the global temperature. So the IPCC really does advocate that we limit global warming to 1.5 degrees. So number 2, this shapes national climate policies and net zero strategies. So governments use IPCC data to set their own carbon budgets, emission reduction targets and adaptation plans. So when a country sets out goals like net zero by 2050, so the UK, for example, the UK government's target is to be net zero by 2050. So that is, I think, for example, for Greater Manchester, it's 2038. We aim to be net zero by 2038. So they can be different. So it's worth to have a look at wherever you are, look at local targets. So it's almost always based on the IPCC pathways, which shows what must happen globally to avoid the worst climate impacts. So it highlights the urgency of action. So the IPCC reports quantify, this is important, this bit. So quantify how quickly emissions must fall and what happens if they don't, by presenting very likely projections of heat waves, storms, sea level rise and ecosystem loss. The IPCC makes the risk impossible for governments and industries to ignore. So it helps countries assess and compare mitigation options. So the IPCC is impartial. It doesn't tell countries what to do, but it evaluates solutions. So looks at renewables, carbon capture, behavioural change, energy efficiency and land management, and assesses their cost, benefits and real world feasibility. So countries base their policies on the IPCC to ensure that they're building effective policies. It also is really important for global accountability. Because the IPCC is neutral and evidence driven, it creates a shared scientific baseline. So countries can argue about politics, but they can't argue about the physics, the science. It's science-based. And the IPCC ensures climate negotiations are grounded in facts, not opinions, which is so important. So just to summarise what the key ideas around the IPCC, its role and what it aims to look at isn't to fix climate change directly, but to make it impossible for governments to claim ignorance. So the IPCC is really important, as it kind of drives governments to think about and be serious about climate policies and their country's impacts on the world in terms of climate change. So its assessments pull together the world's best science, quantify the risks and lay out credible pathways for mitigation and adaptation. So without the IPCC, international climate efforts would lack consistency, shared understanding and scientific legitimacy. So its reports have shaped global climate agreements, guided national policy and set the benchmarks against which climate action is judged. So in short, the IPCC is a scientific backbone of the global response to climate change. Okay, so we've come to the end there. So here are the references. So I hope that's all made sense for you today. So I would really recommend in checking out these references, especially some of the work of the IPCC. Okay, so there's the plenary. So if you want to have a look at the references, you will find them on your Moodle, and any kind of further reading. If you have any questions or queries, please email us at learnerwork@ukversity.co.uk. So the submission for this assignment for this unit is due 2 weeks after completion, in 2 weeks' time. Okay, thank you. Bye-bye.